Computer Science and Engineering Colloquia features accessible talks by leading computer scientists and computer engineers from across the region and around the world.
It's my great pleasure to welcome Charlie Catlett from the University of Chicago. So Charlie has a history of being around major shifts in computing infrastructure. He was at the National Center for Supercomputing Applications at its inception when working on NSFNet, one of several networks that led to the internet, and as teams were building Mosaic, the first web browser, Charlie was working on the first scalable web servers. He was director of the TerraGrid initiative from NSF, which put together the largest combination of scientific computing resources in the world, and he's now in the process of directing and instrumenting another shift in computing infrastructure paradigm, which is out to the edge and out into the urban environment, and that's what he'll talk about today with the Array of Things project. So welcome, Charlie, and we're glad to have you.
Thank you. So thanks for having me. Let me give you a little bit of background on what we're doing. Then most of the time I will just tell you about some fun toys that we're building and why we're building them and what they mean. A couple of years ago, I had the opportunity, that's probably the closest thing to a sabbatical that one could get at a national laboratory, which is that the lab director told me, go find something fun to do, and ideally something that would be an opportunity for the laboratory. So that was about 4 years ago, and I had done high performance computing and other things for a while, but I thought, well, I've been working with architects and trying to figure out how to use tech in buildings to better control energy and understand their behavior. And they got me interested in collections of buildings and cities. I'd also been working with social scientists and policy people and found some of their work quite intriguing about how cities work for people. So I thought, well, let's try to pull together the hard sciences, if you will, at a national laboratory like Argonne, where we have computing, environment, biology, climate, et cetera, materials, sensing, and pull that together with the University of Chicago, which is one of the places on the planet that's really done a lot of work in trying to understand the people aspects of cities, from sociology to finance to public policy, and see if we could create a center within something called the Computation Institute that's joint between the lab and the university. Create a center that's not like this big army of people that work for me, but a bunch of collaborative projects with people from the university and from the laboratory. And also we've ended up pulling in people, I guess as you sort of saw on the title slide, from other universities as well. So we, over time in those several years, did a number of projects and kind of landed on 3 different areas to work in. One of which is just using the increasingly diverse data sources that are there to better understand cities, and ideally then to affect changes in cities that would make them work better for people, not just people trying to park their cars in smart cities, but work better in general. And then as we got into the looking at data, we found some questions that people wanted to ask for which there wasn't data that had sufficient spatial or temporal resolution. And I'll give you some examples of that going forward. And one of the first projects we did was with a 600-acre development down on the south side of Chicago, a former U.S. Steel plant. And we worked with the developers and architects of that site to try to anticipate and give them a tool that would forecast energy use at the site over decades with uncertainties. Well, basically with a couple of knobs that you would turn in terms of the growth of the site, the zoning of the site, and then with various scenarios as far as what the climate would be like over the next 20 or 30 years. Today, what I want to do is just give you a little bit about what we're doing with data science, but spend most of my time telling you about the Array of Things project, which is what I'm spending most of my time on these days on a day-to-day basis. So you've probably all seen portals that look just like this. The city of Seattle has one that looks identical, except it's Seattle instead of Chicago. It's a company here in the Seattle area, or in Seattle, named Socrata, that provides these data portals. And the community that's interested in urban data has done some interesting things with respect to mapping or using GPS tracks. In the middle of the right-hand side there is a snapshot from an animation of snowplows moving through the city of Chicago during a 2-day blizzard. And so, some of that's been useful. We did an analysis of the efficiency of a change in the way garbage was picked up for the city from a district-based to a regular grid-based. And so we were able to tell from GPS tracks whether they drove more miles, and we could tell something about congestion and other things. But ultimately, what's people in cities that are making decisions either to plan for changes or policies or to manage operations of cities, they're looking for prediction and optimization. And a couple of examples of that, in the upper right is some work that originated with Dan Neal at Carnegie Mellon, and then the city got some help from Allstate as a pro bono in some of the data science. But this is a optimization of food safety inspections. And like I would say every project that we're doing with the city of Chicago, it began with some commissioner or person in the city saying, I have this problem, can you help me with it? And it didn't start, including the array of things, didn't start with, I have this solution, tell me how I can help you with it. So in the upper left there, the commissioner for public safety came to the CIO and said, I have 32 inspectors and 15,000 establishments I have to inspect every year. Can you help me do a better job? So they took 30 or so data sets that were some leading indicator value to food safety violations, including past violations, 311 reports of spilled garbage, food safety reports, food poisoning reports, et cetera. They took all these 30 or so leading indicators, developed an algorithm that would rank the different restaurants and food establishments according to their risk of having a food safety violation, just high, medium, and low. And then the commissioner went to her 32 inspectors and said, you guys, for the next 60 days, just do your inspections the normal way. You get your list for the year and you randomly inspect them. You guys over here, we're going to give you a list and you're going to inspect in that order, and we're not going to tell you why you're doing that. And they said, okay. So what you see in the graph there, the blue line is the violations that were found in this 60-day period, and when they were, how soon they were found. The red line trailing behind it by about a week is the normal business as usual random inspections. So that 7.4-day average jump on a food safety violation means that there's a whole week that can go by where somebody might eat in that restaurant and not potentially get food poisoning. So a small optimization, but one that is quite important to public health. The bottom here in the right-hand side, those are Chicago crimes over a multi-year period of time. This is a paper that results of a paper that we just submitted to a journal, and I'll show you what the website looks like to this. But we had a small grant from the Arnold Foundation to work with the former chief data officer for the Chicago Police Department on a crime prediction algorithm based on some of the work he had done in the Chicago Police Department. And we were wanting to ask the question, if we add weather as a leading indicator, do our predictions get better? And it turns out they get way better. And I'll show you in a few minutes what that looks like on a map, because what we do in that project is we take prior crimes in a particular area by census tract. There are 600 and something census tracts for City of Chicago. So for each one of those, we do an hourly prediction from time 0 to 72 hours out based on prior crimes in that place plus weather. And the next project, having done this sort of proof of concept, is to start adding other leading indicators to make those predictions better. And the purpose of making those predictions is for a police department to sit down at the beginning of the shift and sort of plan out their routes based on spatial hotspots in their area. So as we started doing this work with the city and talking with social scientists and others that want to use data about cities, we found that, and I think at least some of you are old enough to remember the internet in the 80s, we found that these open data portals are great in the same sense that anonymous FTP servers were great. They were really great if you knew what data you needed and where it was, but they're not so great at finding data that are just sort of browsing for what data was there. So we got another small grant from the National Science Foundation where we said we think that what's needed is to give scientists a tool to be able to search across these open data portals in some intuitive way, and then having found data to pre-integrate that data in terms of the timeline and the spatial coordinates, because those are not always integrated. And this means that if you look at this sort of notional pie chart, that the scientists would spend more time on the scientific question and less time on finding data and then squeezing it all together. And what that means is not just savings of time, but there are some questions that you're not willing to do all that prep work to ask the question because it's too high of an investment or risk when you don't know if it's a useful question. But if we make the red part of this graph smaller, we can ask more questions, and some of them will be not so useful, and others will be surprisingly useful. So the way we went about search was we said, and this was working with social scientists, we said, how can we build a system that you don't have to be a social science or data scientist to use? You don't have to program in R or anything like that. So we present a map and then a window in time. We say, I'm interested in this polygon, or maybe it's a path that I draw through the map. I'm interested in this period of time. This one says the first 10 months of 2015, and I want to see weekly data. And I hit submit, and I get a list of data sets that are in this geospatial database that are relevant to that area for that period of time. And I click on one of them. In this case, I clicked on 311 calls for streetlight outages. And I get immediately this sort of, is there a temporal signature at all? And what does the spatial signature look like? And I can play around with the spatial signature in different grid sizes from 100 meters out to a couple of kilometers. And then I can refine my query up here. So I can, for example, say, show me car accidents in Manhattan during the month of July when it was raining. And I can filter down to that. And then I can say, great, that's a pretty map, that's a pretty graph, but I just want the data. So I pull the data out and I stick it into whatever tool I want to use to do analysis. The important thing about this system that we built, which is now moving from prototype to something we're actually using with the city of Chicago, is that this is just a skin built on top of the API. I mentioned the crime work earlier, also built on top of this Planario system, only here's what Crimescape is what we call it looks like. So there you have the slider across the top where what I'm showing here is on a particular date in October between 5 and 6 a.m. This is the probability of violent crimes by census tract, and red is obviously bad and green is pretty good. And then I can slide that out to 72 hours or back to 0 hours. Now, I actually used this a couple weekends ago because I was at this event that was a weekend event at Google, and I knew I wasn't getting out of there until like 1 or 2 in the morning. So I thought, well, I'll park close. And I parked in a place that looked fine on the map, but when you actually drove into the parking lot, it was like a scene from The Godfather. It was like somewhere you would take someone, you know, where the end of the scene would be, you know, leave the gun, take the cannoli, right? So I used this to decide whether to walk to my car or take an Uber, and I ended up taking an Uber. But again, this is aimed at using, you know, in this case, just a little bit of data to give some predictive value to a service provider in the city, in this case, the police department. Now, for that work, we were a little bit, I'd say, at a disadvantage because we wanted to take into account weather. And if you talk to police, they will tell you, you know, the first warm spring weekend, we're going to have a shooting somewhere, a rash of shooting somewhere. We don't know where, but we know it happens when the weather gets better. And it turns out there is this effect that we did see in our predictions when there's a certain delta in temperature and we look at rainfall over various periods, and et cetera. But the problem we had with weather is that Chicago only has 6 weather stations from NOAA, and the closest ones to the city are at O'Hare Airport and Midway Airport. So we're doing predictions. So we're trying to do, you know, predictions over here, but the nearest weather station's out here, and it's given us the same measurement for the entire downtown area. So it turns out that this is an example of a question that we want to be able to ask, but the data is not there to ask the question. Another example, which comes up a lot, is we have some parts of not just Chicago, but every major city, where you have parts of the city that are just always have worse air quality than other parts of the city. And you have parts of the city that often correspond to that, where you'll have an incidence of asthma among kids over here that's way, way higher than kids just a half a mile away. And of course, it has something to do with not just air quality, but building stock and things like that. But we don't have data, we do have for building stock, we don't have air quality data, for example, to really be able to tell what's causing these pockets of bad air quality. Furthermore, we have models that can sort of predict where that bad air is, but there aren't any cities that are instrumented, so it's kind of like we have a model for an aircraft wing. We're pretty sure it works because look at the visualization, but we don't have wind tunnel to test to see if the model corresponds to reality. So if you think of the city as a thing you want to model, and you want to model the flow of carbon monoxide through the city, but you don't have anywhere to validate those models, then you're sort of guessing. So we said, we need more data, we need to be able to validate some of these models, so these are the kind of questions we wanted to be able to ask. Now, we were not quite so, I'd say, enlightened when we first started the project. It actually started in a rather innocent way, and that was that, and so by the way, this explains why it's called the Array of Things. We were having this workshop in downtown Chicago with high school students, and we had like 30 students, and they were going to assemble an air quality monitor, design an enclosure for it, and print it and do the maker stuff. And then they were going to place these, they were just going to make like a dozen of them, place them all around the downtown area of the city of Chicago, and then watch the data over a couple weeks. So we thought, this is great. We teach kids to solder, we teach them to program, how to use the Fab Lab stuff, how to collect data and what to do with it. This is like a dream workshop, we thought. And the city was really excited, the chief technology officer, the chief sustainability officer. And we got to that part about putting the sensors out in the city. The kids like walked out with these things and they're like, okay, where do we plug it in? And then how do we plug it into it, because we didn't have wireless, where do we get network? And where do we leave this so that it doesn't get vandalized or stolen? So they all came back, and I went to the city and I said, hey, I think we have found an opportunity where you can help the research community, and by the way, companies and schools, if you just make a way for us to put a bunch of devices throughout the city where there's a hard part of urban sensing, if you will, and there's a relatively easy part. So the easy part is building a gadget. The hard part is that real estate issue of power, internet, and safe place to put it. So my proposal to the city was, can we do the hard part once in a way that we could do the easy part over and over again? So they said, this sounds good. So we started having workshops with scientists from different areas, starting with a group of people that do urban heat island and what cities do to weather. And each time we would have a discussion like, if you could put sensors in the city, what is it that you would want to measure? So the configuration of the Array of Things nodes came out of this like 2 years worth of workshops with the science community, and the building of this team that you see on the right-hand side, actually 4 teams of scientists, all of which have some sort of common sets of things they want to do. One of the interesting things about the third one here is that without that third one, we probably could get by politically a lot easier because we wouldn't need cameras. And when we first started the project, I said, no cameras, it's going to be like, it's like painting a target on our back. There'll be privacy issues all over the place, but we'll listen for wireless devices and we'll just count the addresses. So I thought this was an innocent thing to do. Actually, it was an innocent thing to do. The Chicago Tribune disagreed. So front of the Tribune on a Sunday above the fold, City of Chicago to scoop up big data from your cell phones. So incidentally, just for those of you who aren't from Chicago, we do have occasionally a crime problem in Chicago. On the weekends, the big story is how many people were shot this weekend. So that particular weekend, the CIO was at the gym. This is a true story. The CIO was at the gym. The police commissioner works at the same, or goes to the same gym. She said, normally it's a polite smile because we're sometimes in meetings together, but we don't really know each other. But this particular weekend, he came over with a big grin on his face and thanked her for giving him the weekend off because our project was above the fold and not the crime stuff. So we decided to back off from listening to addresses and counting addresses, partly because we weren't convinced it was going to give us good data. And then we decided to sort of jump out of the frying pan into the fire and go ahead with the camera because we're like, it's already out there, let's just rip the Band-Aid off and see what we can do. So now I would say we have an aspiration that's part of the project, which is that we want to be able to demonstrate the policies and the architecture and the accountability structure that you would need if you were going to put cameras in the public way where you have transparency and where you actually are trusting what the people who own the cameras are doing with them. And that's something we don't have right now, not just because of transparency, but because of the need for a combination of transparency and accountability. So I'll come back to that a little bit later. Timeline is we started a couple of years ago actually trying to see how to build things that could be out in the Arctic or the Amazon River Basin or downtown Chicago where it's expensive or impractical or both to be able to go and hit a reset button when something goes wrong. So resilient systems and thinking about how and why do these things fail in the field. We put, I would say, that sort of generation 1 of Array of Things nodes back in the summer of 2014 out on the roof at Argonne with this very attractive Mylar wrap around the electronics at the bottom, and the sensors are inside what hasn't really changed much at the top there, that sort of beehive-looking thing. It's like a stack of dinner plates upside down, where the ones in the top and the bottom are regular plates, and the ones in the middle have a hole cut out, so you get this cavity, and that's where you stick the sensors, so they're protected from sunlight and direct rain, but still get airflow. Last May, we put not 12, we ended up only putting 9 up on the UChicago campus, looking like that, these things about this big, vacuum formed, hand soldered, hand assembled, a 3D printed vent at the bottom, cheap electronics, really expensive to build because of the labor involved. This year, the plan is beginning in March to deploy 50 of things that look like that one on the pole, and then by the end of the summer to have 200 in the city of Chicago, and then by the summer of 2017 to grow that to 500. They may or may not look like the pretty looking green and yellow one on the right-hand side because we'll probably retain that beehive thing because we'll want to put more sensors in there, and sensors aren't necessarily getting smaller. But that's the general timeline. So we are right here where we're about to pull the trigger on manufacturing the first 75 of these, and our contract with the company that's doing this with us, they say that they can build 450 of them between now and June, and that's way more than we need for Chicago. Therefore, we've got, as I'll mention later, a number of partnerships, including with UW and the city of Seattle, to pilot these things in other places and to expand on some of the capabilities. So after all those workshops, what's inside the box? 2 things here. One is in this, this is an early artist conception, but inside these waterproof boxes under here are the electronics, and then inside this beehive are the sensors. So since this is computer science and EE, you might be interested in what we did on the upper right-hand side. And so we looked at, I'll just give you a few examples of types of failure modes in the field where I wouldn't worry about it so much with, I have Raspberry Pis and Photons and BeagleBones and all sorts of these things, Arduinos in my house, but I'm okay every 6 months or so going and resetting something that goes wrong in the Arduino in my basement or with the Raspberry Pi. But if I put 500 of these up 13 feet up on poles in a city, and even 1% of them fail, it's going to be awkward. So we didn't look at single devices, but even small probabilities of problems we tried to anticipate and then either prevent or recover from. So a couple of examples. First of all, the 2 Odroids there in the middle, and by the way, all these are to scale except for that there, but the components here are roughly to scale. Those are the size of a deck of cards. 4-core ARM Cortex processor in both of them. The one on the left also has an 8-core GPU. So that's what we'll use for onboard image processing. One of the reasons we chose, not the only, but one of the reasons we chose these is because one failure mode is that the SD card that these all run on will have a soft error and then might even have a hard error, at which point you've got a brick. So the Odroids have 2 slots. So we said, great, we can go into the bootloader, we can watch and say, oh, we haven't booted correctly or successfully the last N times, so let's try a different image on, we'll think it's a soft error, try a different image on the same SD card. And if that doesn't work, we'll fail over to an image on the other SD card. So that already gives us increased confidence just from the one kind of failure of an SD card getting too cold or too hot in Chicago summer or winter. Another kind of failure we learned from Intel. They did some things in London with the Galileo, which was their Arduino compatible try to capture the makerspace product. And the first version of that they sent out for evaluation to a bunch of people, ourselves included. But the folks in London deployed these and they put cellular modems on. They found that when the cellular modem signal dropped below a certain amount, the Galileo would boost the power to the modem until it burned it out. So we thought, okay, well, sometimes things go wrong and they start to draw lots of current. So we'll do a couple of things. Those small black boxes, the 6 of them across the middle of that right-hand side board there are current sensors, and the large ones are relays. And then the small black box at the bottom is an Atmel processor, like a $6, but really reliable, resilient processor. So with that board, we're watching what's happening in the rest of the box. And another one of these sort of failure modes are just the thing hangs. And so we've got a heartbeat monitor between these things. That's a 25 hertz heartbeat monitor. There's a real-time clock, which is why there's a coin battery holder there. And then that board has temperature and humidity and vibration inside the sealed box. So when the temperature gets in the summertime too hot for the Odroids or in the wintertime too cold, that little Atmel processor can go, hey guys, put yourselves to sleep. I'll wake you up when it's safe to run again. So we built a number of these kind of things into the upper right. And as it turned out, we added the image processing board after we did the initial design. But it also comes with the sort of nice feature that those things can fail over to each other. And the functions of one can go over to the other to keep the device going. So we now can take 3 hard failures of SD cards, for example, before we go belly up. And we can even lose one of those and still keep the node running. It might be with reduced reliability, or sorry, reduced function, but it'll at least keep running. Okay, so we designed that board in the upper right. We went through a number of generations of hand soldered, and now, not this one, but the next one after this, which looks a little different, but same function, are being produced by a commercial board producer for us. And when we want to respin it, we have a 6 or 8 week turnaround time to get new boards. We designed these 2 boards as well using off-the-shelf commercial sensors that are listed in there. It's at the PM 2.5 is this thing that looks like a stubby stapler. And then this board on the right-hand side is a set of gas sensors from a company called SPEC. They're electrochemical sensors. And they're probably the most uncertain part of the device because nobody has tested these low-cost electrochemical gas sensors at this scale out in these kind of conditions before. It's a relatively new company. But Intel, working with us and the city of Portland and Portland State University, designed that board, which actually has that 70-pin connector on the left because they would have loved it if we put an Edison on there. And we told them, no, we like the Odroids, but we'll take your sensor board. So that's the gas sensors, and you can see the list up there. This has got various light sensors, infrared. And then with the camera and the infrared sensor, there's one pointed sort of, these are 13 feet off the ground, direct wired into street signal light poles, and one pointed down at the streetscape with a 187-degree field of view, and another pointed straight up at the sky, which is of interest to the atmospheric scientists in particular. Yeah, so that's what's inside the box. We are working with Bill, actually, and some others here in the city of Seattle to try out a precipitation monitor. These self-dumping heating buckets are like $500 or $600, and there are infrared precipitation monitors that we're interested in that are more like $40 or $50. Let's see, since I'm talking about pricing, all of the components that you see here, with the exception of the AlphaSense particulate matter sensor, all of these are around $600 worth of parts. This sensor is about $400. To package these, to do all the enclosures, et cetera, is probably going to add about $60 for assembly and a couple $100. We haven't got the final bill yet, but roughly a couple $100 for the enclosures. And part of that is it's $50,000 or $60,000 to do the tooling to be able to injection mold those sensor shields rather than 3D print them, which is thousands of dollars and not very practical. So we are a relatively small group at Argonne working on this. It's a project called Waggle that's run by Pete Beckman and myself and some others. And this is what we've done over several summers and several years. And we've done this, as I mentioned, in response to a set of science workshops. But we also have discovered, as we've been talking to people, that other universities and other cities are interested in measuring their cities, but they might not be interested in doing the design of a resilient urban sensor platform. And they might want to add sensors to our devices. And so we've built now, although we haven't built and won't be built for another month in quantity, the ones that will go out on the street, we built these development kits. This is about the size of a dinner plate. And they've all the components of the node, but obviously not meant to go outside. So these, within the next few weeks, will start going out to partners like UW, where we're looking at, we have probably several dozen groups that are interested in doing a variety of things. Some of them are just saying, hey, we want to deploy your nodes in our city, so we'll help you debug the configuration and management tools. Just send us the unit. We'll try to boot it up in the lab, and we'll tell you how your instructions and procedures work. Other groups are interested, like these guys here, in adding different sensors, and we support standard sensor interfaces, serial I2C, et cetera. And then there's another group that we've just begun to start to try to engage, and that's the computer vision community. So the idea behind this instrument, NSF is funding a 500-node instrument in Chicago as an experimental instrument to observe cities. And what we proposed to NSF was we were building a community instrument, so all the data is free and open, but we also are working toward supporting people downloading modules to these for data processing on the node. And so we want to engage the computer vision community to do some image processing on the node, because for privacy purposes, what we've said in our privacy policy and the way we set this up is that with the exception of the calibration period, all the images that are seen by the node are processed on board and then discarded. So we're not sending video, we're not sending images except for that calibration period. And I have a few things about process later. So these are development kits. We built 25. We have parts for 25 more, and we're going to start shipping those. And very interested in groups that want to collaborate. So an open source platform. This is the final diagram, or set of final diagrams for what you see. That's Pete Beckman on the left there holding, which is the first prototype node. This is the part that took, it was about $2,000 of 3D printing to get that quality and that size. So obviously that's not scalable. It has to be injection molded or stamped. The guy on the far right is a professor from the School of the Art Institute of Chicago, who's an architect and a designer. And so he began working with us 2 years ago about what this thing would look like up on the poles from the point of view of like real people walking by. And so we said, should be conspicuous, maybe friendly looking. We want it to be embedded in a community as an asset and not this thing projected in the community by the university or the city to watch the residents or their environment. But in any case, you can see this sort of 3D puzzle that you go through to build something like this. And that's a picture I just took the other day of that node laying on the table. You can see there's kind of blue tape on it. That is tape that turns white when it gets red, or when it gets wet. And so that was right after we had done the water spray test, the sort of garden hose test. Interestingly enough, the way that our engineers, the way that they tested airflow was to put a smoke detector inside and then blow incense through it. I assume that they were doing like Pink Floyd in the background or something if they're burning incense, but a clever way to test the airflow and see at what point the smoke detector stops going off. So kind of, let me just sort of bump up to the policy and process and intent of this project on a grander scale, and then talk about where these devices will go and how we make that decision in the city of Chicago. I've already mentioned privacy. We felt that transparency, of course, it's already part of what, at least the CIO part, it's already part of what the city of Chicago is aspiring to with all of the open data initiatives. And so already out in GitHub, and there's the GitHub link at the bottom, you can go play around with the software as it is eventually the final designs for the boards that we built and for the 3D enclosures will also go out there for non-commercial use. The transparency is good, so you could go, if you know how to read code, you can go on the web and you can say, yeah, they're actually doing what they say they're doing in the policy. But if you're not a software developer, you're just a normal person in Chicago, that transparency doesn't help you very much. So this is where accountability comes in. It turns out NSF is funding a group at Indiana University to help other NSF projects with cybersecurity and privacy. So we said, hey, can you guys create an independent oversight group that reports to the city of Chicago, and anytime we make a change with respect to privacy, you get to review what we're doing, the privacy risks, mitigation that we're doing, and then you can tell the city whether they should let us do what we're talking about doing. Now, I realize in terms of accountability, it stops somewhere. In this case, it stops with the city. And so if the city wanted to do something, there's no oversight to them except the fact that those are elected officials. So, the turtle has to stop somewhere. I've talked about partnerships with other cities. We now have 18 cities that want to pilot these and that we think will do some of that pilot work this year. There's a long period of time to go through to get permits and legal approval to put things up in the public way. But 18 of them have said, we're ready, send us devices, we want to try them out. And our strategy for working with other cities is not to work directly with the cities, but rather to work with local universities and national laboratories and essentially be technology providers to our peers who then want to work with their city, as opposed to being a vendor of supported hardware and software, which is, we're not at the point where we can even think about doing that at this point in the development process. So that's the idea. And as I already mentioned, all the data in more or less real time, open and free. So early on, we actually were not quite sure how to decide where to put 500 nodes in the city of Chicago because it's 600 square kilometers. And depending on the science team that you talk to, you need a different density. If you talk to the people, the social scientists, the traffic transportation guys, they would want these things on every street corner. Whereas the atmospheric sciences guys, they showed us a map of the city, they drew an X across and they said, if you put 20 or 30 of them on this X, unevenly spaced, that's good for us. You don't have to do a regular grid across the city or anything like that. So I had a few experiences last summer that I would say sort of helped us understand what's the best way to go about this, or at least what we think is the best way, because we're still in the middle of it. And that is, I got a call from Presence Health, which is a healthcare provider on the west side of Chicago. It's a part of Chicago, the west side as well as the south side, where you have very high crime, high unemployment, and some of the more poverty-stricken areas of the city. So Presence Health, the largest Medicare provider in the state, and they said, can we buy some of your nodes because our hospital over on the west side has really a lot of cases of asthma, and we want to put them around the neighborhoods to try to figure this out. And I said, oh, that's really interesting. We could sell them to you, I suppose, but we have 500 of them and we're looking for a place to put them, so why don't we partner with you? Not long after that, I was meeting with several UChicago medical research teams, and they were talking about a cohort study of asthma across the city of Chicago, where they had recruited something like 2,000 families to track their medical history with a particular focus on asthma. And then the city, within a few weeks, said, hey, we're thinking about doing some sustainable green space infrastructure because of urban flooding issues on the west side. So it occurred to me through these conversations that if we start with a concern with residents, concern that residents have, and then we say, okay, if we had better data, is there a science community out there that could give us more insight into that concern if they had better data? And if the answer is yes, then the third question becomes, and if we had more insight, is there some interest on the part of people who make policy and investments, such as local government, to do something about that concern? So now we've from that set of incidents on the west side, we've been sort of using this rubric to determine where to put nodes across the city. The most recent one, not shown on this map, is that Pullman. People know of Pullman coaches. you know, the first refrigerated train cars down in the part of Chicago called Pullman. And that's now which is, by the way, right here, that's now a national monument and a national park, an urban national park. So they called up and they said, can you help us understand traffic flow and people flow in Pullman? And we're like, oh, that sounds really interesting. Do you have a relationship with the community that we could work with? They said, yes, we're working with a community. So we said, okay, we can support what you're interested in testing with our gear, and we'd love to help you with that. So that's a more recent one. The west side you can see up here on the left-hand side. Now on the right-hand side, the two different kinds of icons where we would like to put nodes, the blue ones, little buses. The city is just opening up an express bus service along those east-west streets, one way in each direction. And had we had the array of things 2 years ago, we could start gathering data, but we thought, well, we won't have before data, but we could at least start putting nodes in the downtown area. And then State Street, this one off to the right here, the Business Innovation District, it's called the Chicago Loop Alliance. In cities, there are these groups of building owners and business owners that tax themselves and make investments. They're going to put, or they're already started putting a commercial system for counting pedestrians and vehicles along a 9-block corridor there. So we said, great, we'll put ours in the same place, then we'll have something to compare to, and is our pedestrian or bike counting, lining up with the commercial systems. So I'm going to close this, talking about these other cities. This is a map, it's an evolving map. Boston was just added a couple weeks ago when the CIO for Boston and folks from Harvard and Northeastern called me on the phone and said, sign us up. Atlanta was added about a month ago, same story. A guy in the mayor's office heard about the project and called me, and I said, oh, well, are you talking to the folks at Georgia Tech because they're working with us? And they said, well, no, but we got them on the phone with Georgia Tech, and now we have something going with Boston. Same story with all these. Taipei and Taichung City is sort of an interesting one. That came about in September and illustrates what we're trying to do with the cameras. So the National Laboratory, National Applied Research Lab in Taiwan, they're located in Taichung City. They had a couple of us go down there and do like a workshop on this kind of thing. And they said, let us show you our toys. They have underwater cameras pointed at the reefs. And they are recognizing like different kinds of fish from shape detection. And they have hundreds of cameras across the island because they have a problem with typhoons there. And they have software that looks for rising water and surface flooding that uses actually the same libraries that we support on the node. So we said, can we give you one of those development kits, and can you make your software run on our node so we can point it at the street and see if there's urban street flooding in the Array of Things node camera view? They said, that sounds great. So that's the kind of partnership that all of these are something like that going on. And you can see from the blue ones that there's a number of other conversations that have begun that haven't quite gotten to that point. So anyway, I can take questions. I'll say I was interviewed recently by I'm a University of Illinois at Urbana-Champaign graduate, and I was interviewed by their alumni magazine, and I told them all about this, and they said, okay, now let's talk about what you do to have fun in your spare time. And I said, I thought that's what we were talking about. So I'm happy to talk more about this. So.
Questions for Charlie?
You said the 3D printed prototype of the sort of umbrella shapes cost several $1,000s. Was that due to material cost and printing, or to the cost of the design process and all the failed prints that went into getting a good prototype?
That was a combination of designer time. That was a small part of it, but most of it was that material and the use of a really, really super high-end 3D printer that they use in these. The company that we're working with, PDT is their name. They're a bunch of ex-Motorola guys that do prototypes for Apple and Acer and Samsung and people like that. So they're using like way high-end. For example, their CNC machine is like a $200,000 machine that can CNC over different surfaces and things. So you could do that. You could do that on. We have a fairly high-end 3D printer in our lab. It would take several days not including the ones that fail or stick or don't stick or what have you. So even it's a huge part to 3D print.
There's no doubt that having a lot of sensors in a city is very useful. But the question is the best approach to put out new sensors or to harvest the sensors that are already there? For instance, in Chicago, I'm a meteorologist, and I know there are hundreds of weather observations in Chicago. Forget about the airports, there's all kinds of other networks there. So you can instantly have hundreds if you just collected it. Smartphones are collecting pressure, thousands of them in Chicago. And I go on, but and eventually, virtually all cars are going to have internet connectivity, and you can harvest things off of that. So what I'm saying is, one mode is to put new sensors out, but another mode is to harvest the tremendous density of observations that are out there. And which one's the best way? Is it a good idea to spend a lot of money on these sensors?
So it's a really good question, and there's no, I'm like thrilled with the notion that you're discussing, and there are folks that are doing that. I don't know that it's really cheaper or more expensive or better or worse, but I think of it as complementary. So I think that's an exciting area to get into. We would love, we're working with Brookhaven National Laboratory to put these on top of New York City buses. We want to do the same thing in Chicago. But you're right, cars already have like hundreds of sensors. Cell phones do as well. Part of my answer is having this real estate up on the poles, it's almost not even an interesting question what we're putting up there today. Because with a 15-minute swap out, we can put something up there different next year. My sense is that the sensors that you would have in your phone, apart from the fact that this is not a place to put a particulate matter sensor behind in your pocket, right? But there's ways around that. Whatever sensors I can put into this phone that make economic sense to put into this phone or even into the car, there's another generation or class of sensor that's not cheap enough yet to put into this device. So, as more sensors come into here, we would say our devices are going to be for the larger ones, too big to fit in here, more expensive ones than can put in there. So I actually think these are two really interesting areas, and I would hate to have to choose between them. One more comment about the weather underground and other things is we looked at that data along with our friends that do what you do. And the two things we found were, number one, in city centers, Midtown Manhattan, Chicago Loop, there's not many of them there, because if you live there, you can't open your windows, they're all sealed. The other thing we observed is that, and depending on which one you look at, a lot of them are just crazy wrong or aren't working at all. So we think, as with the mobile sensors, that's a source of data that shouldn't be discounted, but it's a complementary source to what we're trying to do.
Alan?
Well, I really like the attention you've been paying to issues of trust and privacy. I'm still wondering if things are a little messier even than you portrayed. So in the New York Times yesterday, there was a story. This is a report in response to the FBI's interest in having a backdoor to get encrypted data. It said, well, don't worry about it. We're going to have lots and lots of opportunities for surveillance with the new Internet of Things and monitoring. So you don't need to get into encryption. So I think people may look askance at some of these claims about, no, trust us.
Well, I think they should. This is, at a certain level, this is not a completely solvable problem, because whatever you say, people will still have some concern or doubt. This is where the accountability we feel like is going to help us, and that is that there is an external group who is not beholden to us, that is able to look at what we're doing. But is it messy? It's a super messy, and we're about 2 weeks away from publishing the privacy policy for public comment, and we'll get some feedback on that. We had a review. We've been inviting the people that we think will be the most concerned. We've been inviting to come in and advise us. So we've had some really productive discussions with folks from the EFF. We had a review where we had several people from ACLU. We have people from universities coming in. So we're trying to be our own sort of devil's advocate, because I'm sort of an anti-surveillance person myself. So I would like to be able to demonstrate a system that has the advantages of cameras, but that demonstrates a way to do it that is respecting our privacy. But it's a hard area. We may know more after they go up. Well, I'll come back next year and tell you, how it went.
Let me make one quick comment while there's a break, if you're thinking of one last question. If you want to participate in the Seattle side of this project, please let me know. In particular, someone to help us out with the embedded system side or wants to work on sort of attaching this rain gauge sensor and think about that, as well as applications for any of this data that you have in mind. We have a great conversation going on with the city of Seattle through the CTO's office, and they have an enormous commitment to making this project work. So if you're excited about it, come and talk to us. I had one question maybe about the software. You didn't spend too much time on kind of what happens once the data is telemetered or gathered, and I'm steering it towards things that I think about. But do you have thoughts about whether one big mothership in the sky collecting all the data from the world is, will afford certain kinds of questions to be answered, or do you envision more every one of these will be kind of a separate system, and the policies, the questions people are asking are really kind of city specific, and that's good enough?
So I don't know the right answer to whether there should be the sort of Whopper from War Games mothership or whether there should be the web. I suspect it needs to be something in between. And initially, even if we were talking 10,000 nodes, having a single mothership, these are not producing a ton of data. We estimate a gigabyte per month per node on average. So that's kind of in the noise if you look at what's happening in high-performance computing centers. So the mothership is not technically infeasible, and so we're sort of moving in that direction. And when you were there in September, we had a discussion about this, and you said if we go with multiple motherships, we should at least think ahead of time about how they can federate and how you can find things across them and not just let them all grow up without thinking about that. Maybe just backing up about the data. So these are cellular connected. They'll come with a cellular modem and a SIM card from our one of the companies we've just about finalized a deal with, and they'll be in a bundled plan of average gigabytes. So it won't be super expensive to do the data part. So the devices run autonomously. There's no open ports to connect to. This is one of our security designs. Encrypted communication, signed code, VPN on top of that or under that, depending on your view. The data gets reported roughly once or twice a minute. That's a configurable setting. When the nodes report data, they look for instructions using standard Linux code management to keep the code up to date. They can set up a tunnel so we can log in. Then the data goes into a data store where we'll keep data forever, the raw data. And then there'll be two layers of sort of check or validation before the data is published. The first is just a sanity check. Did the temperature really swing by 50 degrees centigrade in a 5-second period? No, so we throw the data out. That's obviously wrong. Or is the temperature really 200 degrees? In an early version, we had a node, and I looked at the setting or the website for the node on University of Chicago campus, and I called up our engineers and I said, hey, either there's a problem with the temperature and humidity, or somebody's pointing a carpet steamer at this thing, right? So there's a validation check there. And then the harder problem, which is actually what I thought you were going to bring up about meteorology, is the harder problem is trusting the data. And how do we know that the carbon monoxide readings from these new electrochemical sensors are actually giving us good data? So that we have this calibration and validation step on top of that that's really not so much a sensor activity, but a scientific and mathematic activity. What we're doing there is partnering with the EPA. We're sending them a unit in March. They've already tested the AlphaSense unit in 3 seasons, but they haven't tested the gas sensors. And then the EPA has said we can co-locate next to their sensor stations so we can at least compare with what the EPA knows. All that data then goes into a database at Argonne, and then there'll be a couple of different places where we pull the data out, probably with a few minutes latency to get through these and to manage load. One of them will be Planario, which I showed earlier. Another will be the City of Chicago data portal. And from there, we'll have APIs for other people to use the data.
All right. Let's thank Charlie one more time.